So let's start. So when we talk about a free body diagram, we need to know how to draw free body diagram and why this is useful. And by using free body diagram, how can this be useful to help us figure out the force and acceleration? So here I have a step-by-step procedure to help you establish a order or a row to draw the free body diagram. The free body diagram is a diagram show all the force on an object. I have a box here, and if there are many force on the box, something like this, and we want to know the net force. What's the net force on the box? To figure out the net force, we need to first move all the force to the center of the mass. Move all the force to the center of mass. So we know there's a center here. Is the center of mass for this box, and then I move all the force. For example, I move this one and start from here, so it goes down, and this one has another force. So this is the second one, and I move this like this, move this like this, this like this, and this like this. So eventually I will have a force diagram like this. So you can see all the force share the same starting point. I have all the force share the same starting point. And this point is the center of the mass. So this is very important. If we draw a diagram like this, for example, I have a box, I give a push, then you draw a force like this. This is not free body diagram. This is a schematic diagram. So to figure out the difference between the schematic diagram and the free body diagram, the only difference is in the free body diagram, all the force is share the same starting point, and this starting point is at the center of the mass. And for the schematic diagram, you can draw any force anywhere, and just to help the reader understand how does the force apply on the box. Okay, so this is the free body diagram. Then the next step is to figure out how many forces there are on the box. So to help you understand or to remember the step, I have an order here, and this order just help you to don't miss anything and when you draw the free body diagram. So the order will be, the first one is gravity. We can call this weight. Everything on the earth should have a weight. So the first force you are going to draw on the free body diagram is gravity. Second one is a normal force. Normal force means if you put the object on the surface and you compress this box and the surface is going to give an elastic force. And the force is perpendicular to the surface, and the value will change, but we need to show the normal force. Third one is friction. Friction is very important during the motion. Sometimes we want to make the problem easy to solve, so we just imagine some frictionless surface. Then we don't need to draw the friction. But in the real case, the friction is not negligible. So we need to draw the friction on the free body diagram. And the friction is opposite to the velocity. This is in the negative velocity direction. Okay. Then the last part will be the external force. The external force includes any force provided by human. So for example, we have a push force, we have the pull force, we have a tension from the rod, or there is any elastic force from the spring, so we have spring force, and so on. So any force provided by different object is called external force. So this is a step. So if we draw the free body diagram, for example, we will think about that. The first one is gravity. So the grad is always the first one, and the label will be W. We represent the weight. And the second one is normal force. Normal force perpendicular to the surface and outside the surface. This is normal force. And friction, if there's friction, then figure out the direction of the friction. Then the last one will be the external force. For example, if I have a push force to give the force on the box, then we have to move the force starting from the center, so it goes to the right. That will be the push force. Okay, so this is the step-by-step procedures to draw the free body diagram. Then let's do some practice and help you to refresh your head and get all the things in mind. So I have two crit here, crit A and crit B. Then they sit at rest and side by side on a frictionless horizontal surface. Okay. This is very important. We don't need to consider the friction. Then they have masses MA and MB respectively. And when there is a horizontal force is applied to crit A, the two crits move off to the right. If there is a force applied to the crit A, and everybody move to the right. So the location for A and B should like this. A and B is sit at rest side by side, and the force is in the horizontal and everything moves to the right. So the force should give in this way. Okay. And there is a surface. Then let's draw the free body diagram for each of the body. For the second one, part B, crit B, it's easy to draw. So we begin with the crit B. So the number one, let's follow the order. The first is gravity. Gravity on the body, on the crit B goes down. This is weight. Okay. Then the second one is the normal force. Normal force on the crit B will be the force to balance the weight. It goes up perpendicular to the surface. So this is normal force. Okay. This is normal force. The second one is normal force. The third one, friction, and this is negligible. So we don't need to draw this. Number four, external. External means the force coming from other object. So the crit A is going to push crit B, and both of the guys are moving to the right. So if the speed goes to the right, there should be a force on the crit B to push B move to the right. So that will be the force from A. Force from the crit A. Force from A to B. Then the force gives the B should towards the right. Then from this free body diagram, you will get three forces in total: gravity, normal force, and the push force from crate A. So this is a free body diagram for the second crate. Then for the first crate, let's see. This is crate A. And let's follow the rule. Gravity, same thing. Normal force, same thing. Then let's see what else. No friction, obviously. But for the external force, we know a horizontal force F is applied to crate A. So we should draw the applied force first. The applied force goes right. This is applied force. But let's think about that. Because A contacts with B, if A push B from the Newton's third law, the B is going to give a reaction force to A, right? So because there is a reaction and action pair force, for the crate B, there is F from A to B. Then in return, on the crate A, there should be a force from B to A. And the strengths are equal, but the direction goes opposite. So the direction goes opposite, it should go to the left. And the label will be the force, pushing force from B to A. Okay, so this is very important. And I think it's very easy to figure out the three. But for the rest of this one, you should think about that. Do we miss anything here? So that's why I draw the free body diagram for crate B first, because after I have crate B, it will remind me of a reaction force on the crate A. Okay, part B, if the magnitude of F is less than the total weight of the two crates, where it causes the crate to move, so if this force is very weak, small, and less than the gravity. So is there still a motion in the horizontal direction? The answer is yes. Because if you check the crate B, in the horizontal direction, there's only a pushing force from A to B. So no matter how large the force is, there's no other force to balance this push force. So even there is a very small force on the crate B and going to the right, the crate B will move. So the answer is yes. No matter how large the force is, there is a motion. But you might think about it in a different way, because in your mind, in the reality, if you want to push something and make this object moving, you should give an efficient force. That means if the force is not large enough, nothing's moving. When we have this experience, we should think about that. Everything in the reality has friction. Because the friction is going to block the motion. So that's why we need to give a sufficient force to move everything. But if this is a frictionless surface, for example, if this surface is made by ice, it's very smooth and everything can slide on the ice. So if there is a very small force on the crate B, then the crate B will still move. So the reason is friction is zero. Then everything will move, even the pushing force is very small. That's part B. Okay, do you have other questions? If there's no question, let's go to the next problem. This problem due last week, and it says there's a chair, and you know the weight, and there's a force, and the direction of the angle is 30 37 degrees below the horizontal. Okay, that means this force is not on the axis. So the chair slide along the floor, and this is not frictionless. Okay, we have to consider the friction, but it doesn't say the direction of the moving. Okay, so we can assume a direction of the motion. Then it will be convenient for us to draw the friction. Okay, so first one, draw free body diagram. There's a chair. Okay, there is a chair, and this chair is on a surface, and the surface has friction. And let's see. Suppose this chair slides to the right. There's a speed for the motion for the chair. Go to the right. Then let's figure out the other force. So let's follow the order. First one, gravity. So gravity goes down. Second one, normal force. Normal force goes up. Okay, this is easy. Number 3, friction. Friction depends on the speed of the direction of speed. Because the speed goes to the right, then the friction is going to encounter the speed, going to prevent the motion, right? So the friction should go to the left. Friction goes to the left. They're going to deaccelerate the motion. Okay, the next one will be external force. External force is the force F, and the direction is a horizontal, has a degree, 33 degree, or 37 degree below the horizontal. So the horizontal, this one, this is X, and 37 degree, so this is 37. Then we finish the periodic diagram. So everything complete. That's part A. Part B. Use the diagram and the Newton's law to calculate the normal force that the floor exerts on the chair. And to figure out this problem, let's think about how can we use Newton's second law to figure out the force. The normal force is in the y direction. So we can define the positive y direction goes up, right? So in y direction, the y direction, there are 3 forces. Normal force, weight, and the y component of the force. Right. So we can separate the force. Follow the parallelogram rule for the force. So we have x component of F and the y component of F. Okay, so we have 3 forces in the y direction, and these 3 forces should be in balance because there's no motion in the y direction. So according to the Newton's second law, we have the net force. It's a net force. I sum all the force in the y direction equals MAY. Equal to MAY. And in the y direction, acceleration is 0. So the net force in the y direction is 0. Okay. Then let's figure out the net force. 3 forces and different direction, then we need to sum them. So let's figure out that normal force, positive. Normal force is positive. Weight goes down, negative. So minus the weight. and y component of the force goes down negative. And the 3 force should give us 0 output, right? Then let's see. The weight equal to mg. The normal force is what we're going to solve. And the y component of force, from the separation, the y component is equal to magnitude of the force times sine 37 degree. This is equal to 0. So the normal force could be solved. We have mg plus f sine 37 degree. Okay, so do you have any question?
How do you know that it's supposed to be like sine 37 degrees and not cosine?
Okay. The y component is this side, right? Not this side. This is y component. And in this triangle, this side is 40. And this angle is 37. So if we are going to calculate the side, this one, if we want to calculate this one, then that will be 40 times sine. If this is a cosine, then we will get this side right here. 37. This is 40. This is a 40 sine. This is a 40 cosine. Right?
Got it. Thank you.
And next one, problem 4.37. 2 crate, and one crate is lighter, the other is heavier. And there is a woman, and the woman push the crate with a larger mass, and both of the crates are connected by a rope, and there's a tension on the rope. Also, the surface is frictionless. So let's see. It says the acceleration for the 6 kilogram crate is 2.5 meter per second square. First question, what's the acceleration of the 4 kilogram crate? What's the acceleration for this one? And it says the acceleration for the 6 kilogram is 2.5. Then what's the acceleration for the 4 kilogram? Okay, so let's see. There is a tension on the string. There's tension. So that means these two crates have the same motion, have the same speed. There is no relative motion. And between the two crates. So this is very important because there's no relative motion. If there's no relative motion between the 4 kilogram mass and the 6 kilogram mass, then they should share the same acceleration. So if there is relative motion, for example, this guy moving this way, this guy moving this way, then they have relative motion, then they don't have the same acceleration, then there shouldn't be a tension between them. So if there's a tension, that means the string is in tight. And when the string is in tight, then the distance between these two crates is a constant. The distance constant, then the speed will be the same and the acceleration will be the same. So part A, the acceleration for the 4 kilogram is equal to the acceleration of 6 kilogram because they don't have relative motion. Then part B, draw free body diagram for the 4 kilogram crate. 4 kilogram crate. And let's follow the order. The first one, gravity, goes down. Second one, normal force, goes up. And the tension is going to give a force to the right. This is tension. Then there's no friction, so the free body diagram is complete. Then let's see, when we have the free body diagram, use the free body diagram and Newton's second law to find the tension T. To find the tension T, okay, T is in the x direction. X direction. So in the x direction, the net force will be only the tension. And according to Newton's second law, the net force equal to MA. MA, the mass is 4 kilogram. The acceleration is 2.5. So that will be 10 Newton. So the tension is 10 Newton. This is part, part B. Okay. Part C, free body diagram for the second crate. The second crate, so right here. So second one, we have gravity, same thing. Normal force, same thing. And there is a pulling force from the woman. So there's a force from the woman. And the tension is action and reaction pair force. So there's a tension on the string to the 4 kilogram mass to the right, then there should be a reaction force from the tension go to the left. So these two tension is the same because they are the action and reaction pair force. Okay, so there are 4 forces on the crate, and let's figure out the tension on the 6 kilogram crate goes to the left because the first crate have the tension to the right. They have the same magnitude, but the direction are the opposite. Then this is free body diagram. Then what's the direction of the net force on the 6 kilogram crate? To figure out the direction of net force, we use Newton's second law. The net force equal to MA. In the vector format, we have arrow on top. So you can find that the net force is parallel to the acceleration. Because the acceleration goes right, so the net force should go right. And you can think about it in this way, because the woman is pulling this box, so everyone move to the right, so the acceleration should go right. Then, which is larger in magnitude, T or F? The net force we know is the sum of T and F. But T and F are antiparallel, and we define the right side is positive direction. So we will have F minus T. This is net force equal to MA. And MA is larger than 1, so we have force larger than the tension. Okay, so because everything moves to the right, so the force on the right will be larger than the force on the left. Then the last part, use the part C and Newton's second law to calculate the magnitude of F. To calculate F, Okay, what's F? Let's go back to the free body diagram. There's F, there's a tension in the X direction, right? So in the X direction, the net force will be, if the positive direction goes right, then we will have F minus T. Then this will be equal to MA. That's Newton's second law. Okay, so the F could be solved by using T plus MA. T is calculated here, 10 Newton plus MA. M is the mass of the crate, so 6 kilogram, acceleration 2.5 meter per second squared. So we have 25 Newton. Do you have any other question? It will be easier for me to understand where you feel confused if you ask me a question. So far we already gave you 2 examples how to use Newton's second law and the free body diagram to solve problem. So I will give you a short summary. So to solve the force or to solve the acceleration, we need to draw free body diagram and the Newton's second law. So first one, to draw the free body diagram, we need to figure out 4 kinds of force. The gravity, normal force, friction, and external force. The external force includes the pull force, push from human beings, and also we have a tension from the string or the spring force, for example. If we connect the box with a spring, then we should consider spring force. They are all external force. So after we have this 4 kinds of force and the free body diagram is done, then figure out the coordinate in the X and the Y. So list all the force on the X-axis and Y-axis. If there is a force has an angle between the horizontal and the vertical, we have to separate this force to get the X component and the Y component. So if there's an angle, if we have a force like this, then we need to calculate X component and Y component. Okay, the second step. So after that, we will have all the force either on the X direction or on the Y direction. So the third one, define the positive direction in the X and Y. Positive. So usually we use right on the X and up on the Y to represent the positive. Okay. Then the number 4 will be sum all the force in either X direction and Y direction. Sum the force in the X and sum the force in the Y. And they have different signs. So sometimes we use a positive, sometimes we use negative. We need to figure out which one is positive, which one is negative. After we sum this force, then we get the net force in each component. Then this will be equal to MA according to Newton's second law. Okay. Then number 5 will be figure out is there any acceleration equal to 0? If you see at rest or constant speed, if you see these words, this phrase, that means the acceleration is 0. So if we have such of this description, then we can set A in that direction is 0. If not, let's figure out what's A equal. Right? The description will tell you the acceleration, how much the acceleration is. After you have the acceleration, then you will go to solve the force unknown. So this is step-by-step procedure to figure out the unknown force in the free body diagram by using the Newton's second law. Okay, to help you digest all these steps, then I gave you more examples. Then how do we use the Newton's second law in the free body diagram to solve the force unknown? Okay. So here I have an example from the homework due yesterday. There is a ball, very heavy, and it says this ball is hanging on steel. There are two steel tables. This steel tables just give this ball at rest. So at rest is very important. That means acceleration is 0. So let's draw the free body diagram to figure out the tension A and the tension B. So the free body diagram shows that the first should be the gravity. Gravity. Don't forget this one. Second one is normal force. There's no surface, so there's no normal force. Friction, no friction. So the last one will be the external force. The external force are two tensions. These two tensions, one is from the tension from string A, the other will be the force on the string B. The string A give a tension to the left, and the string give a tension to the upright. Okay. So this is the free body diagram, and direction should along the string. Then let's figure out the value of each tension. Because the three forces are in balance, so we are going to solve the equation. And we need to figure out the x component and the y component. Okay. So I define the positive direction, and I find that there is one force not on the x, either x direction or y direction. So I have to separate the tension B to get the x component and the y component. So I separate them, then I get the tension B of x and the tension B of y. Okay, then in each direction, I have two forces. In the x direction, I have net force. The net force will be the tension B of x minus the tension A, equal to MA in the x direction. Okay. In the y direction, the net force will be equal to the tension B in the y, this is a positive, minus the weight, mg, equal to MAY. And we know the acceleration is 0, so they cancel. They are 0. So we have tension B in the x direction equal to the tension A. Tension B of the y component equal to the weight. Okay. And we also know the angle. The angle we have here is 40 degrees. So in this triangle, we have 40 degrees. And this side is tension B of x. This side is tension B of Y. So to get the tension B, we need to use this equation. So from this equation, we solve tension B, Y component. So we have Y component. Then to get X component, we will use this value. X component equal to the Y component times tangent 40 degree. So, so after we have this expression, we can solve the tension B of X. And we know from the first equation, this one, the tension B, X component equal to tension A. So let's do the value, do some value job here. So the A, let's see, the mass is 3620. So the weight, tension B will be equal to hold on, let me see, how large is this? Here, tension B equal to mg equal to 3620 times 9.8. That will be around 3.6 times 10 to the 4 Newton. Then this is a tension B Y component. Then the tension B X component will be equal to this one times tangent 40 degree. Then we will get 4.6 times 10 to the 4 Newton. Hold on, I got it right. Got it wrong. That will be 3.0. Okay, 3.0 times 10 to the 4 Newton. This is a tension A. Okay, do you have any other question?
I was just wondering, why did you use tangent there for tangent?
Tangent? So do you know the definition of tangent?
Yes.
That will be this one over this one. Right?
Right.
Okay, so to get the TBX, we just use the TBY multiplied by the tangent 40 degree. Okay, did I answer your question?
Yes, thank you.
Okay, so I think this is some knowledge from the geometry. If you feel confused about the math, I think you can try to remind you the tangent theta, cosine theta, and the sine theta, the definition. Then that will be easy for you to figure out the angle. Okay, so this is the problem 5.6. Then I have one more problem. Let me go here. Okay. So there is a weight and connect in a string, but there are two forces to bend the string, F1 and F2. And to figure out the F1 and F2, we only know the weight and we have the angle. So when we have the angle and we have the weight, we can figure out the F. Okay. So let's see. And for this point, we have three forces. The first one is the weight. This one is F2. And this one is a tension, unknown. Okay. To figure out the F2, and we only need to separate the tension in the X component and the Y component. And in the X direction, say the X, this one, this is T of X, is T of Y. Then we have F2 equal to T of X. And we also know that the T of Y equal to the weight. This is in the Y direction, X direction, and the weight is 60. And we also know one more thing is the Tx equal to Ty, because the degree, the angle here is 45 degree. 45 degree. Then the X component and Y component are equivalent, because Ty equal to the Tx times tangent 45 degree. Then tangent 45 degree is equal to 1. So we have this one. Then you will find that the F2 is equal to the weight. Okay. So this is a solution for the 5.8. And you can do the same thing for the F1. So I just delete this one. And I think today I will finish here. But at the end of class, I have an announcement. So the first one is, let me see. This Thursday, I have a second quiz. So I think you can check your course site, the schedule. This Thursday, we have the second quiz. And the quiz will be the free body diagram and Newton's second law. And I will give you 10 minutes at the end of class and to finish the quiz. And the same thing, after you finish the quiz, take a photo and convert it into a PDF file, then upload on the course site. So this is a quiz. And after the class on Thursday, I will have office hour. And if you have any question, like the math, how to find the cosine function and how to get the component, you can ask me in the office hour. Okay. So this is what I'm going to do today. If you don't have other questions, you can sign up.
Thank you.
Thank you.